Hello guys, we are back from spring break and we are continuing on in chapter 29 today, okay? And we're still looking, well actually, we are in we're in the 4th edition, and in the 4th edition, what we're in is chapter 26. Okay, I know it says chapter 29, but it's chapter 26 in the edition we're in. So let's kind of remind ourselves about electric fields, electrical potential, and think about how they relate, okay? Really, electric fields and electrical potential are two ways to represent a disturbance in space caused by charged particles. Okay, let me kind of scroll up here. Now, if we think about force, a particle experiences a force because it's in an electric field. Okay, a region of space, okay, because an electric field has a voltage associated with it. That voltage is associated with electrical potential energy, which all comes back to force. So force, electrical potential energy, voltage, okay, its electrical potential, and the electric field are all interrelated. Remember, I have to have an object to experience the force, a charged object. I have to have a charged object to have an electrical potential energy. The electric field and the electrical potential are everywhere in a region of space where there's a charged particle or charged particles causing it. Okay? Now, if we're in a uniform electric field, one where the electric field is everywhere the same in a region in space, we know that force is equal to Q, or you could say Q sub T, the test charge, times the electric field. So remember, if the point charge is positive, the force is going to point in the same direction as the electric field. If it's negative, it's going to point in the opposite. Okay? Change in electrical potential is equal to the negative of work done by the electric field, so minus delta K, which is minus QE S initial minus QE S final. Okay? And remember, the lower S value is toward the negative plate. Or you could say that the change in electrical potential equals QT times E times delta S, or minus W electric delta K. Now, change in electrical potential energy, electrical potential is equal to E times delta S. So we know, okay, that change in electrical potential is equal to change in electrical potential energy divided by Q test. So when I divide Q test out, remember that means that it only depends on our source charge. If we are inside a parallel plate capacitor, and we're going to spend quite a bit of time with parallel plate capacitors, the strength of the electric field is equal to eta divided by epsilon 0, which is the same as Q divided by epsilon 0A. Remember, Q over A, total charge divided by plate area. So delta V is equal to E times D, which would mean Q times D over epsilon 0A, where D is the separation between the plates. Okay? Now, all of this, okay, has to do with the parallel plate capacitor. Parallel plate capacitor. If we have a point charge, okay, we know that as we move out from a point charge as our source charge, that the strength of the electric field changes. Okay? remember it's KQS, the charge of the source, over R squared, or QS over 4 pi epsilon 0 or R squared. So as I move out from the point charge causing our electric field, the electric field drops off as a factor of R squared. That means our equal potential surfaces, if we're looking at voltage, okay, are not going to be equally spaced. So, when we assign V an electrical potential value, okay, at a specific point in space, we need to decide where our zero electrical potential is going to be. By convention, when we're looking at a point charge, the 0 point for electrical potential is set at infinity. Okay? So V at a point in space is equal to K QS over R. So notice, if the QS is negative, then the potential in closer to the source charge is going to be a larger negative value, which means a lower potential. If it's a positive test charge, I'm going to get a larger positive value when I'm in closer, which would mean a higher potential. So if you can remember back to when you took chemistry and you looked at the energy values for electrons in the orbitals around a nucleus, you'll notice they have negative values because you're bringing a negative, well, electrical potential energies are negative in close because you've got a positive nucleus and you've got a negative electron coming in close to it. So, we create electric fields and electrical potentials by creating charge separation or by gathering charge up into a point charge. Okay? Now, I'll have one of these out when you come in for lab. It's a Van de Graaff generator. And in a Van de Graaff generator, we've got a metal hollow sphere on top, and inside of it, we have a rubber belt that's moving, and down here we're going to have a corona charge maker, which is going to deposit charge on the belt. When it comes up to the top, there are brushes here that moves that charge onto the dome. And we create then a charged conductor. And this charged conductor, and see there's the collector. When we put the charge up here, the charge builds the electric field in this region around the conductor builds, and then we can make sparks jump. Okay? The Van de Graaff generator, by the way, was invented here in Tuscaloosa. Okay? So, there's also the Wimshurst machine. I'm also going to have this guy out for you to play with. It's another mechanical way to separate charge, and we're going to do that by moving plates in opposite directions and using a combination of friction and metal conductors. The third way to separate charge, which is one you can carry around with you, and I bet everybody has one sitting nearby because their phone is nearby, is a battery. And a battery uses chemical energy to create charge separation. Now, we're going to concentrate in on batteries. Okay? Now, your book talks about the battery as being a charge escalator. It's a very simplistic way to look at it. Okay? And as you go from the negative side of the battery to the positive side of the battery, you can think about positive charge being carried up toward the positive into the battery, which means that from the negative side to the positive side, there's an increasing electrical potential energy. Because remember, we normally set the negative plate is always going to be our lowest potential energy, our positive plate is going to be our highest potential energy. and the electrical potential, delta V, across the battery, okay, has to do with the chemical reaction and how much charge it can quote unquote lift. Okay? Now guys, in the real world, when we're in chemistry and we're talking about what's really being moved, you can think of it not as positive particles going up, but negative particles is coming down. Okay? Negative particles are shifted toward the negative pole. So, the battery uses chemical potential energy to lift the charge to create charge separation. That means we generate electrical potential energy and we generate electrical potential. For an ideal battery, the change in electrical potential energy is equal to the work chemical. Okay? Now, this is where we get the term EMF. EMF stands for electromotive force. It's given the little symbol of epsilon, not epsilon zero, just epsilon. And it's associated with batteries, and it's a measure of the amount of work per unit charge needed to create charge separation. So the electrical potential, the EMF, is equal to work chemical divided by Q. Now, if we had a perfect battery, the voltage, or the change in electrical potential, not potential energy, electrical potential, is going to equal E. But if you've ever used a battery and touched it afterwards, you know that it heats up. So the actual electrical potential of the battery is always a little bit less than the chemical work divided by the charge being shifted. Okay? So when we work with batteries, the terminal voltage is always less than the EMF because the internal resistance of the battery takes some of the chemical energy and converts it into heat, and it's lost. So when we're labeling a battery's electrical potential, okay, what we see is the terminal voltage. This is always less than the EMF per unit charge. Now, let's think about taking batteries, and we talk about hooking things up from here on out in series or parallel. Series means one after the other. So what we have here are two batteries hooked in series. Okay? Now notice that it's negative, positive, negative, positive. These are hooked in series, and they're hooked so that they're, you think about boosting positive charge to here and then picking it up and boosting it to here. So when they're in series, we add their voltages together. Okay? So if this was a 5-volt battery and this was a 9-volt battery, then delta V here would be 9 volts plus 5 volts, and it would be a 14-volt electrical potential from one side to the other. But if I now hook them up like this, so I have the two negatives together and the positives opposite each other. If this was my 5-volt and this was my 9-volt, they're now opposite. So I would go 9 volts plus a minus 5 volts, which would give me a delta V of plus 4 volts. That's why it's important to pay attention to how you're hooking your batteries up. Okay? So if we look at this guy, okay, I have a 3 volt, and then this one's backwards, and then a 3 volt, so we have, 3 volts plus a minus 1 volt plus 3 volts. So that would be plus 5 volts. Okay? Now, you can also put batteries in parallel with each other. Parallel, okay, would mean side by side. So I connect them like this. Okay, so there's wires connecting those, and then, you know, this goes out to whatever kind of load we put in there. Okay, so that's parallel. When we put batteries in parallel, they're going to have the same potential across them. Okay, same electrical potential, so this would be a 9 volt and a 9 volt. The potential from this side to this side is still 9 volts. Okay, but what we're going to be able to do is, since we have 2 batteries pushing in the same direction, it's like having 2 escalators, you can move more charge. Okay, so you actually get a larger current. So, just a reminder, electrical potential and electric fields are 2 different ways to describe the same thing. Essentially, that disturbance in space caused by some source charge. Okay? And we know that delta V is equal to E delta S if I'm in a parallel plate capacitor. So this is for a parallel, come on, go up where I want you. Parallel plate capacitor. Okay, for a parallel plate capacitor. Now, if we kind of turn things around a little bit, we can say the magnitude of an electric field at a point in space is equal to dV ds, or delta V delta S if I'm dealing with a uniform electric field. Okay? So if I know something about the change in electrical potential, I can learn something about the electrical potential energy. Okay? To make this interpretation valid, we need to remember that E always points in the direction of decrease in voltage, electrical potential. E is always perpendicular to any equal potential surface, and if you move along an equal potential surface, there is no change in electric field. Now, let's look at this electric field. The electric field is pointing in the positive Y direction, and it's uniform. Okay, so what I have essentially is a parallel plate capacitor here. Now, electric fields always point toward the negative plate and away from the positive plate. So that means that the electrical potential should be at its highest here and move toward a lower value as we go this direction, in the positive Y direction. Okay? Now, if we look at these graphs, okay, this would be the 0, this is the positive Y direction. So I know that as I go in the positive Y direction, my electrical potential should go down. Okay? This one doesn't work because I move in the positive Y direction, the electrical potential is going up. Here it's constant, that can't happen. Here I started out at 0 at my 0 Y, and it becomes more negative. Now, by convention, we usually don't put the 0 point at the positive plate, but you could. And if you did, moving toward the negative plate, the electrical potential would go down. So the answer here is C. Okay. Now, let's look at this figure. Okay. Here we don't have a uniform electric field, but we do have equal potential surfaces. Okay? Now, I can use equal potential surfaces to help me figure out the strength of the electric field in a region in space. If we look at point 1, okay, then this is a centimeter, this is a centimeter. From each side here, between these two equal potential surfaces, we have a 2 centimeter spacing, and we have a 100-volt drop. So 100 volts divided by 2 times 10 to the minus 2 meters. And let me grab my calculator. Well, 100 divided by 2, that's going to give me 50. 50 over 10 to the minus 2. So I've got 50 over, back over here. Go back where you belong. That's 50 divided by 10 to the minus 2. So it's 0.50 as my electric field strength at that point. Okay? So let me write that neater. Erase. So at point 1, I have an electrical potential energy of 0.5 joules. Okay? And it's going to point in this direction. Now here at point 2, notice my equal potential surfaces are further apart. Here it's going to be 4. So 100 divided by 4 is 25. So here the electrical potential is 0.25 joules. It points in that direction. Now I'm not drawing it to scale. It should be shorter. So notice here, stronger electrical potential energy, a larger electrical potential energy. Here are smaller electrical potential energy because the fields are further apart. Now if we look here at point 3, what I've got is, that's 1, well here, 1, 2, 3, approximately. So I would get a 0.33 joule as our electrical potential energy. And again, it's going to want to point inward. Okay? So even though I'm moving between the same the same equal potential surfaces, because they're differently spaced as we move through here, we have different electrical potential energies. Okay? Now, let's think about problem 6 at the end of the chapter. No, wait a minute. Problem 6. Yeah, let's look at problem 6, the end of the chapter. Okay, if we look at problem 6, at the end of the chapter, it says two flat parallel plates, 2.5 centimeters apart, are kept at potentials of 20 volts and 35 volts. Estimate the electric field strength between them. Okay? So, hold on a second. I'm just going to write it out here. So if I look at finding the strength of the electric field, E, it's just going to be the change in voltage, and the voltages were 20 and 35. So 35 volts minus 20 volts. And we're told that the plates on this parallel plate capacitor are 2.5 centimeters apart. So 2.5 times 10 to the minus 2 meters. So 15 volts divided by 2.5 times 10 to the minus 2 meters. Now you guys can pop through the division very quickly. Okay, so 15 divided by 2.5 exp2 negative, so I get 600 volts per meter, which is 600 joules. I just realized, guys, that I divided through by 10 to the 2 up there instead of 10 to the minus 2. So 100 divided by 2 exp2 negative. This should be 5,000 joules, not 0.5. Okay, I'm off by a factor of 4. I apologize. Okay, guys, let's scroll up. Now, this is the stop and think problem, okay? On page 720 in your book, it's stop and think 26.2. Now, if I look at my electric field here, I want to choose the equal potential surfaces that line up with this. Now, if I look at it, the strength of the electric field is increasing. Okay? That means that the spacing between the equal potential surfaces is increasing. Excuse me. The strength of the equal potential surfaces has to be decreasing. Because to have a stronger electric field, I have to have my equal potential surfaces closer together. And electric field vectors always point in the direction of decreasing electrical potential. So I can knock A and D out here because they're equally spaced. Okay? I can knock B and E out here because they are unequally spaced, but as I'm going in this direction, they're getting further apart, which means the electric field should be getting weaker. So I'm down to C and F. And the correct answer here would be C, because we want the electric field vectors to point in the direction of decreasing electrical potential. So the correct answer, C. Now, we've come to Kirchhoff's loop rule. Okay, we're getting ready, guys, to start launching into circuits. And one of the rules that we're going to use when we're looking at circuits is Kirchhoff's loop rule. It says the sum of the electrical potential differences, the voltages, around a closed loop is 0. So delta V for a loop is the sum of the delta V's for all the parts, which always have to sum up to be 0. So if I looked at going from point 1 here to point D, that would be plus 40 volts. So 1 to D plus 40 volts. D to point 2 is 0 volts because I'm moving along the same equal potential surface. If I went from 2 to C, that would be a minus 10 volts. If I went from C to B, at 0 volts. If I go from B to A, that's a minus 10 volts. And if I go from A back to 1, that's 0 volts. If you add that up, excuse me, I erase that. This should be 20 volts because I went from 20 to 40. So 20 minus 10 minus 10, that all adds up to 0 volts. So when I go around the circuit, starting at one place and coming back, I get 20 volts. Now guys, notice down here it says that potential difference along path, the red path, along the blue path is both 20 volts. So anytime I go between two equal potential surfaces, it doesn't matter how I get there, I have the same potential difference. Okay, now let's look at problem 16 at the end of the chapter. Okay guys, if we look at problem 16 here, it says what's the potential difference, delta V for 3 going to 4? Well, 30 plus 50 plus delta V 3, 4 minus 60 has to be 0. Well, 30 plus 50, 5, 6, 7, 8, that's 80. 80 minus 60 is 20, so this has to be a minus 20 because when we make the complete loop, we have to get back to where we started.